Okay, this is the video for Lab 6, Reactions and Solubility. This is going to be a longer video, but that's because there is so much going on this week in lab. And even if you've had it in lecture, this is where we're tying it all together, and it's really important that you have a good grasp of it. Now, the first thing we're going to start with is signs of a chemical reaction. Now, for the last few weeks in lab, you've been dealing with reactions, so this will be something that we can tie into what you've already seen. Then we're going to classify reactions according to the 5 main types. Now, depending on your textbook, a lot of times they just mention types of reactions, and they don't really talk about how it can be both a main type of reaction and it can show you something else can happen. And so we've kind of designed this lab to go from random types of reactions into you can have this classification of reaction, but hey, it can also do this. And so we're really going to be trying to tie these two types of reactions or characterizations of reactions together. We're specifically going to focus, this should be over, on oxidation states and solubility for precipitation reactions, just because those are the hardest ones to really identify. Now, in terms of a chemical reaction, let's think about what you guys did when you had calcium, a piece of calcium in a test tube, and you added in some acid. Instantly, you saw some bubbling, meaning that you were producing a gas. Those of you that were holding the test tube also seemed to immediately note, hey, there's a color change. So those are really two signs of a chemical reaction that you saw 2 weeks in a row. You saw it with the reactions of calcium, and you saw it with the percent composition lab. And then you also have seen in one of those labs the change in pH because you used the litmus paper to determine if the solution was acidic or basic. And you found that the addition of calcium to water was indeed basic, meaning it was producing a base. So these 3 you have seen already. Now, I also have up here color change as a sign of a chemical reaction. Now, if you're in my lecture, you've heard we don't mean blue solution plus a yellow solution makes a green solution. No, it is a counterintuitive color change that you cannot explain except for the fact that a chemical reaction is happening. Meaning you add a clear colorless and maybe a pink clear solution together, and you get something like a cloudy yellow. Okay, you will see a specific color change that you cannot explain any way except through a reaction. And finally, down here we have precipitation of a solid. Now, this does not mean you have a solid and a liquid, you add them together, and you get a solution. We want to see a precipitation specifically of a compound on the product side. We do not count things like calcium metal or last week you used aluminum metal. We are only counting solid compounds that are formed as a product, okay? Last week in lab you saw the formation of copper solid. It's not a compound, it is not a precipitation reaction. So let's go into the 5 main types of reactions. The first is synthesis. For synthesis you have 2 specific reactants. You react them to make one product. So here we have sodium and chlorine. That's 2 different things making one product. For the most part, these are elements, but occasionally one of these reactants could be a compound as well. Second is decomposition. Decomposition is exactly the opposite of synthesis. You have one reactant that breaks down into 2 specific products. The most common things to do this are chlorates or carbonates. Those will easily break down to give either oxygen or carbon dioxide gas. Occasionally, You'll also see it with like hydrogen peroxide or other peroxides splitting apart to give oxygen as a product. And this would be water over here. These are the hardest to really observe in lab, primarily because they usually take time. I'm not going to say that you won't see them in lab, but be aware that the best indication that it is happening for you is going to be the production of this gas. Combustion, there we go, is going to take some organic or carbon-containing compound, react it with oxygen, usually in the presence of a flame, to produce carbon dioxide and water vapor. Again, production of a gas is usually consistent with combustion. Here, this is propane, so just like in your gas grill, you burn it with oxygen, you make carbon dioxide and water vapor. Single replacement, here you have an element and a compound, and you react it to produce a new element and a new compound. Single replacement means something like this element comes in and replaces, there we go, this element to make copper go with the anion copper nitrate and silver metal. This is very similar to what you guys did in lab with copper 2 chloride dihydrate and aluminum metal. The fact that you are forming a solid does not mean that this is a precipitate. It just means it is a single replacement reaction. We'll talk about precipitation in a minute. You guys also witnessed single replacement when you added magnesium or calcium to water and you produced calcium hydroxide or magnesium hydroxide and hydrogen gas. Again, you can kind of tell gas forming is a pretty common sign of chemical reaction. Double replacement reactions, you have two compounds as reactants, and they're basically going to switch partners to make your product. I've seen this explained two ways in textbooks. The first is if you look at the first and the last ions in your reactants, you'll get a compound A and D on the product side, and then the two inner, B and C, are going to go together on the other side. Remember, cations always go first, so it's A and D and C and B. The other way you can do it is you can think about A, I need my eraser. You can think about A coming in and kicking C out of this compound and replacing it. So A is now going to go with D. C is going to come over here, kick A out, and form with B. So examples of this are something like silver nitrate reacting with sodium chloride to produce silver chloride and sodium nitrate, or HCl plus NaOH forming salt and water. You can already kind of see this is a precipitation reaction because we have a solid on the right. This right here is an acid-base reaction because acid and base are on the left. Now, these are our five main categories. When we have a reaction, for the most part, it is going to happen in water because it's easy to have in water the specific things floating around. You're going to come in more contact than having a solid state. It's really hard in when you're in solid form to have any kind of motion that would allow for molecules to come in contact with each other to allow for a reaction. That's why, for example, you guys will always store meats and foods in the freezer. If it's in that solid state, the colder state, the less movement you have among molecules, the less decomposition and reactions you have, the better it is for your food preservation. In addition, gas molecules move really quick, so that would be awesome to watch a chemical reaction happening as a gas. The problem with that is most gases have to be at a higher temperature than what we really want you guys dealing with in lab. So for that reason, we do almost everything in water. So the five main categories of reaction can be further classified based off what you're seeing in lab. So for example, you could see the production of a gas. So up here, we had, let's just talk about decomposition. One reactant going to two products. This is a decomposition reaction that is also a gas evolving reaction. Acid-base. These are going to be double displacement or double replacement reactions where you have an acid and a base reacting together. Those tend to be the two easiest ones to identify right away. Now, for example, if we go back to the same decomposition reaction, this guy right here is a decomposition reaction that is a gas evolving reaction, and yet it's also a redox reaction. But unless we go through the oxidation states and what it means to be oxidation or reduction or redox reactions, you're not going to see that right away. You have to actually kind of figure it out. We also need to talk about solubility rules to talk about precipitants. Now, precipitation reactions, you're going to see the formation of a solid as a product. Now, you're not going to see a big chunk of solid fall out, but you're going to see your solution get kind of cloudy. Go away. And so that cloudy solution is kind of like muddy water. Eventually, the mud will settle down and you will get a solid at the bottom of your thing. So let's talk about precipitation for a second. In order to talk about precipitants and for you guys to be able to identify what that precipitant in your reaction is, we need to talk about solubility rules. So I've got it here two ways because I know some students really like it in a picture form and others really prefer it in a more text or flashcard form. So I'm going to read it from up here and then I'm going to tell you how my table works down here. So nitrates, group 1 metals, and ammonium and acetate compounds are always soluble, period. Nitrate compounds are soluble, no exceptions. Group 1 metals, ammonium, and acetate compounds are soluble. There's nothing in here that can make those things insoluble. Chlorine, bromine, and iodides. Okay, let me restate it. Chlorides, bromides, iodides are soluble unless they're paired with silver, mercury, or lead, in which case they become insoluble. So down here I have chlorides, bromides, and iodides over here in the soluble column. However, if they get paired with one of these, they become insoluble. So I've got the arrow pointing in this direction. So for example, silver chloride, silver bromide, and silver iodide are insoluble. These guys are soluble until they come in contact with these ions and it forces it out of solution. Sulfates are soluble unless they're paired with barium, calcium, mercury, or lead, in which case they become insoluble. So sulfates will be soluble unless they touch barium, calcium, mercury, or lead. So if barium and sulfate form a compound, barium sulfate is insoluble. Calcium sulfate is not soluble. Mercury sulfate is insoluble. Lead sulfate is insoluble. Every other cation with sulfate is soluble. Hydroxides are not soluble unless they're paired with barium, calcium, or any ion that is always soluble. So hydroxide wants to precipitate out. However, if you put it with barium, calcium, or a group 1 metal, or ammonium, they become soluble. Sodium hydroxide, you guys have used that in lab, and it's always clear. It's never got that cloudy tinge to it, so it's always soluble. So sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide, those are always going to be soluble. Group 1 metals and ammonium can also force sulfates, carbonates, chromates, and phosphates to be soluble. So these guys are always insoluble unless they're paired with one of these, in which case it forces it to go to the soluble side. Hopefully that helps you. Now guys, keep in mind, your textbook is always going to give you more rules. I think some textbooks will go as high as like 25 different rules. The lab we used to use had something like 25 solubility rules there. And your textbook will also mention things like being marginally soluble or slightly soluble. For our purposes this semester, we are going to say it is either soluble or it's not. You don't worry about something that is slightly soluble until you get to 112, okay? So let's talk about this for a second. And actually, I'm going to go ahead and fix this real quick. Better. Okay. Hopefully that sign won't show up anymore. So let's look at these reactions. Barium chloride plus sodium sulfate reacts to form sodium chloride and barium sulfate. Let's first look at what the main type of reaction is. It can't be synthesis because we have two compounds here, and there's two products here. It's not two things forming one. It can't be decomposition because you have two reactants instead of one breaking apart to two. It's not combustion because you're not reacting with oxygen to form CO2 and water. And it can't be single replacement because you don't have a compound and an element. These are both compounds. So this must be double replacement. Now, to get full credit in lab, you have to classify it as both a main type and an aqueous type. So we've got double replacement, and let's look. Is this going to be gas evolving? I doubt very seriously salt will form a gas, and same with this salt. So it's not gas evolving. As far as acid and base, I don't see an acid or a base over here, much less both, so it's not acid-base. We haven't gotten to redox yet, so let's just assume it's not redox. So it probably must be precipitate. So we're going to call this a double replacement reaction that is also a precipitation reaction. You know, never was good at spelling. Now, I'm not going to worry about balancing. You may have to do that in class, but let's just first look at solubility. Barium chloride. Well, chlorides are soluble unless there was silver, mercury, or lead. So this guy must be soluble. So we're going to add an AQ here. Sodium sulfate. This is a group 1 metal. It has to be soluble. NaCl, group 1 metal, always soluble. Barium sulfate. Sulfates are soluble. Oh, unless they're with barium. So this must be our solid or our precipitate. So this is our precipitate. Now we can actually take this a step further and talk about our net ionic equation. So let's write our molecular equation. Our molecular equation is going to give us the mole-to-mole ratio of our reactants and our products and the states in which they're present. So if we were going to balance this, and I would encourage you to pause and balance on your own, we have BaCl, NaSO4. There's 1, 2, 2, and 1. On this side we have 1, 1, 1, and 1. So to fix that, all we need to do is add a 2 here. Now, this is our complete ionic equation, and I would read this as 1 mole of barium chloride reacts with sodium sulfate to produce 2 moles of sodium chloride and 1 mole of barium sulfate. So this is our molecular equation. Sometimes it's more important to talk about what is actually present. And to do that, we're going to write our complete ionic equation, where we write each of these components in the form that they're actually there. So for example, barium chloride is aqueous. What that really means is it's not a barium chloride floating around, barium with 2 chlorines. Instead, it breaks apart into aqueous ions. So we really have barium 2+, aqueous, plus 2 chloride ions, aqueous, plus 2 sodium ions, plus a sulfate ion. Ideally my arrows would line up, but that's life for right now. On this side we have 2 Na ions because it's aqueous, and 2 chloride ions. Anytime you have a solid, liquid, or gas, it stays together as a molecule. So we also have a barium sulfate, solid, floating around. Now, it's great to talk about the complete ionic equation. However, chemists are lazy. We really only want to talk about what's changing, what's really going on. And so we're going to get rid of our spectator ions, the things that are the same on both sides, and then we're going to write the net change. So if you look, sodium is the same. We have 2 sodium ions on both sides of the equation. Same thing with our chlorides. So we're going to rewrite our net ionic equation as barium 2 plus aqueous plus sulfate 2 minus aqueous reacting to produce barium sulfate solid. So we've got our precipitate, we've got our net ionic equation. That's kind of what you're going to be doing here. Down here I actually give you a balanced equation. Copper 2 chloride reacting with 1 mole of potassium sulfide to produce copper 2 sulfide plus 2 moles of potassium chloride. Okay, so let's look. The main type of reaction here, it can't be synthesis because I have 2 things on the product side. It can't be decomposition because I have 2 reactants. It can't be combustion because I'm not reacting with oxygen to make CO2 and water. It can't be single replacement because I have 2 compounds over here. So it must be double replacement. Honestly, guys, precipitation reactions are always going to be double replacement. Not all double replacement reactions are precipitation, though. So now let's classify it the rest of the way. Is this gas evolving? Probably not. I don't see anything that would form a gas here. Not oxygen gas or hydrogen gas or CO2. Is it acid-base? Well, copper 2 chloride is not an acid or a base, so no. Same thing here. You need an acid and a base to have an acid-base reaction. Again, we haven't gotten to redox, so we're just going to assume it's not redox yet. But it is going to be a precipitation. So in lab, you would classify this as a double replacement and a precipitation reaction. So let's find our precipitate. Chlorides are soluble unless they're with those 3. Give me one. Okay, so let's talk about, this second reaction. We have copper 2 chloride reacting with potassium sulfide to produce copper 2 sulfide and potassium chloride. If we go back, well, first of all, this is balanced, so yay. Let's find our precipitant. Now remember, a precipitant has to be on the product side, but we're going to actually go ahead and find the state of matter for all of these. Chlorides are soluble unless there was silver, mercury, or lead, so this guy has to be aqueous. Group 1 metal makes the sulfide soluble. Sulfides are insoluble. Copper cannot change this, so this is going to be our solid or our precipitate. Group 1 metal chlorides both want to be aqueous. So this is our molecular equation. Let's go ahead and do our net ionic. Now remember our complete ionic. Now remember, our complete ionic is going to show everything in the state that it's there. So we're going to have, because this is aqueous, we really have a copper 2 plus floating around, plus 2 chloride ions, plus 2 potassium ions, plus a sulfide ion. And remember, our solid stays together, so we have CuS solid plus 2 potassium ions because this is aqueous, and 2 chloride ions because that's aqueous. To find our net ionic equation, we're going to get rid of our spectator, the things that are the same on both sides, which are our chlorides and our potassiums. So our net ionic is Cu2 plus aqueous reacting with sulfides aqueous to produce CuS solid. So that kind of gives you an idea of the precipitation reactions. In terms of redox, redox reactions occur when there's a transfer of electrons or a change in oxidation state. So in terms of oxidation states or oxidation numbers, the only way to really do this, guys, is just to do flashcards. The oxidation state of any element in its native form is 0. So remember, H2O2 are always going to be diatomic. So H2, the H is going to be 0. O2, the O would be 0. Na metal would be 0. If oxygen is in any compound, whether it's CO2 or water or something, it's always going to have an oxidation state of -2. It does change in the presence of a peroxide, and then it would be a -1. Oxidation state of hydrogen in a compound, like in water, is +1, unless it's in a metal hydride, in which case it's -1. Oxidation state of most elements in the compound is going to be the same as the charge of the ion they would form. Group 1, Group 2, Group 3. Group 1 metals are always going to have an oxidation state of +1 in a compound, +2 in a compound for Group 2. Group 3 metals like aluminum is going to be 3+ in a compound. Exceptions come into groups 4 and 8, such as carbon, xenon, and also rows 3 down. Specifically, guys, look for phosphorus, sulfur. I don't remember exactly, but if you see nitrogen can also be a little different if it's in a compound. Now, the great thing is the sum of the oxidation numbers for all atoms in a neutral compound have to add up to be 0. And the sum for anything in an ion has to add up to be equal to the charge. So if you have something like NO3, like the nitrate ion, all of the oxidation states here have to add up to be -1. The oxidation states of hydrogen and oxygen and water have to add up to be 0 because this is neutral. So let's look at this. We're going to classify these reactions completely, okay? Now, we have 2 reactants, 1 thing as a product. So this is a synthesis reaction. We know it's not decomposition because there's not 1 reactant and 2 products. It's not combustion, not single or double replacement, it's synthesis. Now in terms of the aqueous reactions, actually we're not going to do it further than that because of what this is. Well, yeah, no, we're just not going to do it. Let's look at the oxidation numbers here. We have element by itself, so it's 0. Chlorine by itself, so it's 0. In this compound, we're going to make a table. Atom, number, oxidation state, and total. Because this is a neutral compound, it has to add up to be 0. We've got sodium and chlorine. Inside this compound, there's 1 of each. Sodium is in a group 1 metal, so it's probably going to be +1. So overall, 1 times 1 is a total positive of +1. To make it neutral, our total negative has to be -1. So the oxidation state on this single chlorine is 1-. So Na goes from 0 to +1, and Cl goes from 0 to -1. So this is indeed a redox reaction. Honestly, this right here should say aqueous, and so it would not be precipitation, it's not acid-base, it's not gas evolving, it's just synthesis and redox. Down here, this is a decomposition reaction. 1 reactant forming 2 products. Now, this is not acid-base. KCl is always soluble, so it's not precipitation. It is gas evolving, it's producing oxygen. And it is also going to be redox, but let's go ahead and see how I know that. Here, we have potassium chlorate decomposing to potassium chloride and oxygen gas. Now, oxygen by itself is going to have an oxidation number of 0. K in a compound is a main group metal, so it's going to be +1. If I make a table, atom, number, oxidation state, and total. In potassium chlorate, we could do this all as an atom, but let's just do the chlorate ion by itself. So chlorate has chlorine and oxygen, and its charge is -1. So we've got 1 chlorine and 3 oxygens. Oxygen in any compound is going to be -2 unless it's a peroxide. That gives us a total negative of -6. To add up to be -1, this has to be a +5. So chlorine here is going to be plus 5. Oops. So chlorine is plus 5, oxygen is minus 2. Over here, K and Cl has to add up to be 0, one of each. This is plus 1. The only way to cancel it is if chlorine is minus 1. So K doesn't change. However, chlorine goes from plus 5 to minus 1. It is reduced in this reaction. Oxygen goes from minus 2 to 0. It's oxidized in this reaction. So we do have a redox reaction here. So to get full credit for this reaction in that part of your data section, you would have to say main type, decomposition, and both of these aqueous categories. So let's look at these. Type of reaction. In terms of our main type, it is not synthesis. It's not decomposition because we have two things on both sides. It's not combustion. It's not double replacement because we don't have compounds as every option. So this is single replacement. In terms of our secondary type, or aqueous type, it's not acid-base. We do see a change in pH because you guys did that litmus test. However, it is not an acid-base reaction because you don't have an acid plus a base reacting. It's not, actually, it is gas evolving. It is not precipitation because magnesium hydroxide is soluble, or at least I have it here that way. So yes, it is for this reaction. So we're also going to see if this is oxidation. Magnesium starts off as 0 because it's by itself. Hydrogen is 0 because it's by itself. Atom, number, oxidation state, and total. For water, it has to add up to be 0. We have hydrogen and oxygen, 2 and 1. Oxygen in a compound is minus 2. Hydrogen is plus 1, so they cancel. This is plus 1, minus 2. Plus 1, minus 2, because it's in a compound. That's just the rule. To cancel this, magnesium would end up being plus 2. So magnesium goes from 0 to plus 2, so it's being oxidized. And hydrogen goes from plus 1 down to 0, so it's being reduced. So this is also a redox reaction. If you were to find this, and I'm going to challenge you guys to do this, for nitrate, anytime you have nitrate, please hit pause and try this on your own before you listen to the answer. Nitrate, you have 1 nitrogen, 3 oxygens. Has to add up to be minus 1 because that's your charge. Oxygen's always minus 2, gives you minus 6. Has to be plus 5 on the nitrogen. So plus 5 minus 2. This is plus 1 because it's a group 1. To cancel, this is going to be minus 1. Now over here, this is nitrate, so it stays the same as plus 5 minus 2. Anywhere you have a nitrate ion, those oxidation states are going to be the same. Group 1 metal is plus 1. Inside this compound, I don't know if you remember, but silver is always plus 1 in terms of a charge, so its oxidation is going to be plus 1, which means chlorine has to be minus 1. So this is a double replacement reaction that is not an acid-base, it's not a gas evolving, and there's no change in redox numbers. Silver's plus 1, sodium's plus 1, nitrogen's plus 5 on both sides, and oxygen's minus 2. The only thing that this is a precipitation reaction. So remember when you are doing this lab, what you are going to be doing is you're going to be mixing 2 reactants. You're going to be looking for those 5 categories of, or 5 signs of a chemical reaction. Did it change temperature? You're going to tell that by putting your finger on the bottom of the well, not putting your finger in the chemicals. You're going to look for a pH change using either pH or litmus paper, depending on your drawer. You're going to be looking for change in temperature, change of pH. You're going to be looking for a color change. You're going to be looking for a precipitant, which means you're looking for it to get cloudy. Eventually it will settle down, but for the first part you're just going to see it getting cloudy first. And you're going to be looking for bubbling. So look carefully, guys. When you're dealing with a few drops, you're only going to see 1 or 2 bubbles. So you need to pay attention to see that. Once you know for sure that a chemical reaction has taken place, you're going to classify it. What is the reaction? Is it a synthesis, decomposition, combustion, single, or double replacement? Then you're going to further categorize it based on redox, acid-base, precipitation, or gas evolving. So really, you're going to be tying together everything in this one lab.